Hello and welcome to Chapter 17, which is about galaxies. Galaxies are classified based on Hubble classifications that are basically based on their shape, and their shape happens to be dependent on the way that they are formed. There are spiral galaxies, barred spiral galaxies, lenticular galaxies, elliptical galaxies, and irregular galaxies, which don't really fit any of these classification schemes. Spiral galaxies usually have a central bulge ballooning out the galaxy's disk. Spirals are arched lanes of interstellar clouds spreading out from the bulge, and the more tightly wound the spiral, the larger the bulge. Typically, they contain about 100 billion stars and have a diameter of about 10 to the fifth light years. Spiral galaxies are further classified as SA, SB, or SC galaxies, depending on the size of the bulge and how tightly wound they are, with SA being the most tightly wound galaxies or spiral galaxies, and SC galaxies being much less tightly wound, as we see in these pictures. You also have flocculent versus grand design spirals based on how contained the spirals are in each other and how many lanes they have in between them. As for how they are formed, consider a galaxy so young that it has not yet formed spiral arms. Stars began forming in one of its giant molecular clouds. The radiation and winds from these stars compress the nearby interstellar gas, triggering the formation of additional stars. Moreover, massive stars quickly explode as supernovae and produce shockwaves with further compressed surrounding gases until it is Jeans unstable. This gas collapses and forms new stars. Shockwaves are very powerful compressions of the gas, like the sonic booms created by lightning, the snap of a whip, or a supersonic aircraft. Thus, as new stars trigger the birth of still other stars, the star-forming regions grow, a process called self-propagating star formation. The continuing birth of stars accounts for spiral arms and flocculent spiral galaxies. The galaxy's differential rotations, inner regions orbit faster than outer regions, drags the inner edge of each young region ahead of its outer edge, spreading the star-forming region into a spiral arm. You also see these spiral density waves where if you drop a pebble into water, it will send out waves circularly, but if you rotate the water as well as just dropping the pebble in, then you will see spirals start to form together. And what will happen is that no matter what the differential rotation is, they won't wind up like you would see if all you were talking about was the differential rotation causing a spiral. It would just increasingly wind up the more time passes. But if you have these spiral density waves, then the mathematics of them cause there to be push out and pressure waves, which cause there to be the spiral arms that we see in galaxies rather than an ever-tightening spiral that we would see if we just were talking about differential rotation. In addition to spiral galaxies, you also have barred spiral galaxies, such as the Milky Way. Spiral galaxies with a bar of stars and gas crossing through the central bulge is what a barred spiral galaxy is, and we're going to get into kind of the shape of those in a later graphic. But bars form in some disk galaxies when stars near the center of these galaxies that were originally following circular paths are pulled into more elliptical orbits. When enough stars are in highly elliptical orbits, they create the spars in barred spiral galaxies. These stars then gravitationally attract gas into the same orbits. Some of this gas is channeled towards the supermassive black holes residing in the center of most, if not all, spiral galaxies. Observations reveal that about 70% of nearby spiral galaxies have bars, while only 20% of the more distant spiral galaxies do. The further way that we see things, the longer the light from them has been traveling towards us. Since light travels at a finite speed, this means that the further out objects are from Earth, the farther back in time we are seeing them. The fact that fewer of the more distant galaxies have bars indicates that the number of barred spiral galaxies is increasing. For the next classification, lenticular galaxies, a few disk galaxies, both unbarred and barred, have bulges but lack spiral arms. These spiral-free disk galaxies are classified as lenticular galaxies because they look like lenses. Unbarred lenticulars are labeled S0, while barred lenticulars are labeled SB0. Giant elliptical galaxies containing some 10 trillion solar masses are rare compared to other types of galaxy, whereas dwarf elliptical galaxies are extremely common. Dwarf ellipticals contain so few stars, only a few million, that we see these galaxies as nearly transparent. Because we can actually see straight through the center of dwarf elliptical galaxies and out the end of one side, distant ones are hard to detect. Hubble subdivided elliptical galaxies depending on how round they look. The roundest elliptical galaxy are called E0 galaxies, where the most elongated are E7 galaxies. The latter are about 3 times longer than they are wide. Elliptical galaxies of intermediate elongation are numbered E1 to E6. With the following showing an E0, I believe, an E3, and an E6 galaxy, where the E0 is just a sphere, and the E6 galaxy is very elliptical, very squashed out compared to the E0. Despite their extremely low stellar content, supermassive black holes are being discovered in ultra-compact dwarf galaxies. The galaxy M60's UCD1 has an estimated 140 million stars in a volume of only 300 light-years across. This is only about 1/500th of the diameter of the Milky Way. Several theories have been proposed to explain the existence of ultra-compact dwarf galaxies. One is that these were once larger galaxies that lost stars to the gravitational attraction with other galaxies. 2, they formed from streams of stars pulled out of larger galaxies as a result of galaxy-galaxy collisions. And 3, they formed early in the life of the universe in environments where star-forming gas was tidally removed from them early in their lives, limiting the number of stars they contain. The last Hubble classification is irregular galaxies. So irregular galaxies with numerous OB associations and only hints of organized structure are denoted as irregular 1, and occasionally irregulars are observed that appear highly distorted and completely asymmetrical, as though created by collisions between galaxies or by violent activity in their nuclei. These galaxies are denoted irregular 2. Ultra-diffuse galaxies. In 1984, another class of galaxy was first observed, called ultra-diffuse galaxies. They typically are the same size as the Milky Way, but they emit only 1% of as much light as our galaxy. Nevertheless, their total masses are often greater than more commonly observed galaxies. They also typically have about 7 times as many globular clusters as other galaxies with the same luminosity. So, kind of arbitrarily, Edwin Hubble came up with a classification scheme where ellipticals go to S0, which branches off into SA, SB, and SC, or the spiral galaxies in SBA, SBB, and SBC, or the barred spiral galaxies. With the exception of dwarf ellipticals, galaxies form from smaller ensembles of stars, gas, and dust. The underlying dark matter that clumped together in the young universe drew this matter toward it, often assisted by supermassive black holes that formed in the life of the universe. These black holes became the nuclei of the galaxies. In most cases, the more massive the black hole, the larger a disk central bulge. Recent observations show that it often took several billion years for disk galaxies to accumulate most of their gas and settle down into the stable star-forming systems we see today. Normal or unbarred spiral galaxies form when the swirling eddies of gas-rich matter collide and form disks centered on an especially massive black hole and lots of dark matter. When the amount of dark matter and the mass of the central black hole were too low, the matter of the central regions and the disk had bar-shaped orbits, creating the early barred spiral galaxies. When the collision of galaxy-forming gases led to especially rapid star formation, the resulting galaxies were elliptical or irregular. Giant elliptical galaxies were and still are formed by the collision of 2 spiral galaxies of any type. Galaxy collisions do not occur in pairs. Stéphan's quartet, discovered in 1877 by the French astronomer Édouard Stéphan, is a group of 5 galaxies bound together. 4 of its members are undergoing multiple collisions with each other. They will eventually merge to form a single giant elliptical galaxy. Galaxies cluster together, and these clusters cluster into superclusters. There are an estimated 10 million in the observable universe. These data reveal that most superclusters are located in the intersection of enormous filaments along which smaller concentrations of galaxies and clusters of galaxies, as well as intergalactic gas and dust, are found. Between these filaments are voids in which a few galaxies are observed. These voids typically measure between 100 million and 400 million light years in diameter. Besides the occasional galaxy or cluster of galaxy, observations reveal that some voids contain hydrogen clouds, while others may be subdivided by strings of dim galaxies. Interestingly, observations of the location of the nearest 12 or 120,000 galaxies suggest that the Milky Way and the rest of our local group of galaxies is located deep in a void. To better understand the filamentary structure of the universe, massive computer simulations are done to recreate that structure and follow the evolution of galaxies in it. Both simulations and observations suggest that one major source of star formation over the course of the universe is gas and filaments flowing into galaxies, and this is also a 2-degree field galaxy survey, which isn't simulation, but is an actual observation of the structure of the universe around us, based on two complementary or two bipolar observations on either side of the planet and the Milky Way galaxy. A cluster of galaxies is said to either be a poor cluster or a rich cluster, depending on whether it contains less than or more than 1,000 galaxies. For example, the Milky Way galaxy, the Andromeda galaxy, and the large and small Magellanic clouds belong to a poor cluster called the local group. The local group contains roughly 50 galaxies, over a third of which are dwarf ellipticals. Regular clusters are spherical, with a concentration of galaxies at their center due to billions of years of gravitational interactions. However, irregular clusters are irregular. Stars colliding is rare, but galaxies' huge clouds, interstellar gas, and dust are much more likely to collide together. A violent collision can strip both galaxies and their interstellar gas and dust. This happens because the stars and the two galaxies pass by each other and emerge as two separate galaxies, but the gas and dust of the two galaxies collide and stop each other. As a result, the gas and dust remain at the collision site as the stars depart. The energy associated with the collision heats the gas and dust to extremely high temperatures. This process is a major source of the hot intergalactic gas often observed in rich irregular clusters. Supernovae of stars and dwarf galaxies also contribute, as gas is not strong enough to trap it. Starburst galaxies are characterized by bright centers surrounded by clouds of warm interstellar gas, indicating a recent vigorous episode of starbirth. Their warm dust is so abundant that starburst galaxies are among the most luminous objects in the universe at infrared wavelengths. Gravitational interactions between colliding galaxies can also result in millions of stars being hurled out into intergalactic space along huge arcing streams. Many astronomers suspect that giant ellipticals are the product of both galactic mergers and cannibalism, including spiral-spiral collisions. Observations reveal that giant galaxies typically occupy the center of rich clusters. Once formed, giant ellipticals can continue to grow because smaller galaxies are often located around them. As they pass through the extended halo of a giant elliptical, these smaller galaxies slow down and are eventually cannibalized by the larger galaxy. And as with the Milky Way, no cluster of galaxies contains enough visible matter to stay bound together. Therefore, we think that it has to have something to do with dark matter. We are also able to see distant galaxies through a process called gravitational lensing. Gravitational lensing has been observed in a variety of regions of the electromagnetic spectrum. The cluster of galaxies mentioned earlier in the book, not here, has survived as a gravitational lens that has provided astronomers with images of a variety of more distant galaxies. Some of these galaxies would not be visible without lensing, where lensing occurs in a similar way to how lensing occurs in actual lenses where light is focused from parallel rays coming through a lens to a more specific area so that you can see magnified vision. And in the same way that light is bent by gravitational pull, or in that same way, the light is bent by a gravitational pull, which means that it acts as a lens to allow us to see more distant galaxies. And then the redshifts of superclusters indicate that the universe is indeed expanding. The information can be stated as a simple formula called the Hubble-Lemaitre law, where the recessional velocity is equal to a constant, which is called h naught, or the Hubble constant, times the distance, where h naught is equal to 73.5 plus or minus 1.6 kilometers per second per milliparsec, which is a unit of 1 over a second, or 1 over time, because kilometers and milliparsecs are both units of measurement for length. Where we see that the velocity depends on how far out you are linearly, where the farther out you are, the more velocity you have, and this is a direct relationship with the constant of h naught combined, telling you how much velocity there is for a given distance.